work. Welcome to all the speakers and the participants. We have an exciting lineup. And so I don't want, we're probably over the start time, so I won't hold Matt back, but just a few words. Matt is an expert in the field of algorithmic game theory, and his research interests broadly span economics and computation. Matt's a faculty member at Princeton University. He did his PhD at MIT, followed by a postdoc at the Simons Institute. And we decided to keep introductions short, so I won't go on, and I'll hand the mic over to Matt, who will tell us some of his exciting work on combinatorial.
Awesome. I have, I think, this works? It works. Okay, cool. And I'm also one of the co-organizers, so I'll also say thanks again to everyone who's here and also to the speakers who agreed to present. So I'm going to give a talk on recent results on the communication complexity of combinatorial auctions. And it's going to cover several papers. So maybe quickly just read through my co-authors is Frederick Cho and Qianfan Zhang, who are both PhD students at Princeton, Shiri Ron, who just finished her PhD at Weizmann, and Clay Thomas, who is a PhD student at Princeton. And then Mark Braverman, who's here, Jeming Mao, Separ Asadi, Rishikanta Barkar, and Raghavan Saxena. And okay, so I realize that there are people from like, math and econ and CS and maybe eventually OR in the room. So I just want to say, like, what's the style of this talk? So I'm not going to give any complete proofs. I'm going to give one framework that I will overview that may feel a little bit technical. To the extent that the talk will be technically challenging to follow, it'll be because there's going to be a lot of definitions. So just be prepared. So it's all going to be the same line. It's all going to be on communication complexity of combinatorial auctions. But there's going to be, variants of the model, variants of the results, see some statements of algorithms. So some of the definitions, to the extent that it's challenging, that's why. And then I'm going to sneak in one quick story about Mark, because one of these papers was joint with him somewhere in the middle. Okay, so what are combinatorial auctions? So there's a single seller, and they've got a set of items to sell. And then there's a set of bidders who are each interested in the items. And the bidders have a valuation function over sets of items. So they have, for each possible set of items they can get, they have a non-negative value if they got exactly that set. And then what's going to happen, the bidders are going to participate in some possibly interactive protocol. They're going to send messages back and forth with the auctioneer. And at the end of the protocol, the auctioneer is going to say, based on the messages I've sent, I would like to give each bidder some set. These have to be disjoint because he's only got one copy of each fruit. And then he can also charge them some prices. Okay, so this is a combinatorial auction. For this entire talk, the goal is going to be just to maximize the welfare. So what I mean by that is the goal is to find among all partitions of the items, the one that is this, yes, is to maximize the sum of the values. So this is summing over all players, their value for the set they get. And then also throughout the talk, I'm going to be talking a lot about approximation algorithms. And so this is just saying that you get some alpha fraction of the best you could have done. Okay, and so this is, like Shivangi said, my background is in, I'm a computer scientist, but I do a lot of work at the intersection with economics. And so the setting that I'm going to be eventually most interested in is that these players, my co-authors, are not benevolent people who are there just to help me solve my problem. They are hoping to get the sets they like best, and they're hoping to pay as little as possible. And so I need to incentivize them to participate in the protocol in the first place. And so a protocol would be nice if it has this property that we call truthful, which means that for each player, they don't need to know anything about anyone else's valuation. As long as everyone else has some valuation and participates in the protocol in a way consistent with some valuation, then they are incentivized to participate in the protocol the way I asked them to as well. Okay, this is a fairly restrictive property. And so I'm asking that every player, even if they don't know anyone else's valuation, they are incentivized to follow the protocol the way I asked. Okay, and then the reason this is strong is because it should hold no matter what the valuations are, and when they don't know what anyone else's valuations are, so they don't know what the other players are going to do. Okay, and then the last thing that's going to be a constraint throughout the entire talk is I would like the protocol to be communication efficient. So what do I mean by that? So in principle, everyone has a valuation function that is a list of 2 to the m different numbers. So you just have a list of numbers, which is what's their value for each set they could get. And I would like to not learn that entire list of 2 to the m numbers. I would like to learn significantly less information and still be able to get a good allocation. So formally, I would like only some polynomial in the number of bidders and the number of items, bits of communication to happen. And I would like to be able to use only that information to get a good allocation. Okay, so that's the problem. I just want to do one very quick slide. So I think you can find everything I'm going to say interesting without knowing any of these definitions, but it may be, nicer to just know, what these terms mean. They're not complicated. So I'm going to talk about, well, I'd like to solve this problem, assuming that the functions are submodular. So what does submodular mean? It means that when I add an item to a smaller set, that is more useful than adding an item to a larger set. I'll also talk about fractionally subadditive valuations. I think the first bullet is easier to remember. Is just that I have a collection of additive functions, and your value for a set takes the maximum over all additive functions and outputs that. So an additive function just says you have a value for each item. And when I give you a set, you sum your values for each item. And subadditive just means that my value for the union of 2 sets is less than their sum. And then monotone is what you would expect. It just says you get more stuff. So there's no other restrictions. You get more stuff, you're happier. Okay, so I'm going to use these terms, but if you don't remember what they are, that's fine. I'm not going to actually use any of these properties because I'm not proving anything. Okay, so why did I get interested in this problem? So I think within computer science, and especially the CS-Econ interface, this has become one of the primary lenses through which we studied the following question. So are truthful mechanisms as powerful as algorithms? And what I mean by that is if I give you a computational problem and I design an algorithm for it, I would say, okay, that makes me feel good. But what if I need to solve the same problem with, like in a combinatorial auction, participants who aren't just going to tell me the input, they're going to try and manipulate the algorithm to the best of their ability. And so I'd like to know, well, I have an algorithm. Does that mean I can always design a truthful mechanism? I just need to work harder? Or are there some problems that I can design algorithms for, but not truthful mechanisms? And the combinatorial auctions have become kind of like the natural lens through which to think about this. And that's because A, economists have been thinking about combinatorial auctions before computer scientists started talking to them. And B, computer scientists have been thinking about very similar algorithmic problems before they got interested in economics as well. So it has a lot of interest from both sides, and so it retained a lot of interest at the intersection. Okay, and this is like a super general question, and so like any question that's that overarching, you should expect the answer to not just be a simple yes or no. The answer is it depends. And a better question to ask is, when are truthful mechanisms as powerful as algorithms? And I'll give you some quick yes instances for this. So one of the coolest results from auction theory is what's called the Vickery-Clark-Groves mechanism. And so these are 3 economists. And I'm going to phrase their result in a computer sciencey language. And what they showed is that if you can optimally maximize welfare, so if you can solve the welfare maximizing problem exactly, then you have a truthful mechanism. And so what they showed specifically is if you just take that algorithm and query it n+1 times, you can figure out how to do everything in a way that incentivizes everyone to participate as you were hoping. Okay, and so if you don't care about communication or any kind of efficiency, this is amazing and fully solves the problem. And if you care about communication, then unfortunately, this tells you nothing, because all of the valuation classes I just said, none of them can you actually solve the welfare maximization problem exactly in poly communication. So you have nothing to input to this reduction. And this is just one other example that if you insist on your mechanism working for arbitrary monotone valuations, and you're okay with like randomized truthful mechanisms, then we happen to know that if you want it to hold in the absolute worst case and you're okay with randomization, then the best mechanisms are as good as the best algorithm. So that's one example of a case where they're just as powerful. On the other hand, we also have huge gaps. And so I'll just fill in, there's going to be two parts to each of these. And I'm going to tell you what we know about state-of-the-art algorithms with polycommunication and state-of-the-art deterministic truthful mechanisms. So for any of these somewhat restricted classes, we have really good algorithms. So these are constant factor approximations. And in particular, for these two cases, we know these are exactly the right constant. So a half is the absolute best you can do. There, you can't do a half plus epsilon, and 1 minus 1 over e is the best you can do for those. And the best deterministic truthful mechanism we have is a 1 over root m approximation. So that's much worse than a constant. And for arbitrary valuations, I said on the previous slide, the best you can do with an algorithm is 1 over root m. And if you want a deterministic truthful mechanism, the best you can do, this is actually barely better than trivial. So an M approximation you can get by just bundling all the items together and giving them to the same person. You can do slightly better. So you can save a root log M. Okay, so what I would take away from this is that there are pretty significant gaps between the best algorithms and the best mechanisms that we know across all these settings. And prior to what I'm going to tell you in this talk, we didn't know whether any of those gaps were real. So what I mean by that is that even though the best algorithms are significantly better than the best mechanisms, we didn't know whether there needed to be any gap at all. So for all we knew, there was a 1 minus 1 over e approximate deterministic truthful mechanism for fractionally subadditive, a half approximation for subadditive, and root m for monotone, and all of that. And then I included here, there's like, there's like some related results that are kind of in this direction. So I put a little bit of an asterisk there that if you're very curious, you can ask me about afterwards, but I would still say this is an accurate statement that there were no separations. So the takeaway, so I hope at this point that maybe gives like a little bit of an intro to like, okay, there's a natural sounding combinatorics problem, it has a natural econ perspective too. And hopefully you are motivated by the fact that there are enormous gaps between what we can do with algorithms and mechanisms, and we don't know whether those gaps should exist at all. Okay, so now I'm going to transition into telling you some of the results. And like I said, this is going to be a little bit of a flurry of some definitions and some results. So there's going to be two directions I'm going to talk about. Each direction is going to have two subparts. Okay, so just be prepared for that. And so the first direction is I'm going to tell you about tight guarantees for a class of mechanisms. So this is not tight guarantees on what any mechanism can do, but tight guarantees on what a popular class can do. And for this particular class that I'll define in a second, the reason I would argue that's interesting is because every single state-of-the-art deterministic mechanism happens to fall in this class. So so these really are proving the limits of everything we know how to do right now, but it doesn't prove the limits of something totally outside the box that we haven't thought of yet. And then for the second direction, I'm going to give you much weaker lower bounds, but some lower bounds nonetheless on what you can do with any deterministic mechanism. Okay, so let me dive into this. And so let me now tell you a little bit more about this awesome Vickrey-Clark-Groves mechanism. And I should maybe add, sorry, if you're not an economist, another reason to find this super cool. So Vickrey is a Nobel Prize winner, and his contributions to auction theory were, the main reason that he got it. And this is one of his big contributions to auction theory. So I told you that the Vickrey-Clark-Groves mechanism was super cool, and that you can take any optimal algorithm and turn it into a truthful mechanism. And I told you there's a drawback, which is that it requires exponential communication to actually optimize anything. And there's a catch to that drawback, which is that actually their reduction is so general that you can apply it to any welfare maximization problem, even if it is super, super, super contrived. Okay, so what do I mean by that? So even though I can't maximize welfare exactly, I could maximize welfare subject to artificially restricted allocations. So for example, what if I said, I'm not going to consider all allocations. There's too many allocations, but I will consider all allocations that keep all the items together and give all the items to the same bidder. So that's something I can find the best one. I can ask every bidder, please tell me one number, which is how much value would you get if I gave you everything? I can find the largest number. That I can do in polycommunication. That's easy. And VCG says, well, if you can do that, then I can give you a truthful mechanism, but it's going to give, it's going to give all the items to the same bidder. And there are other things I can be creative with this too. I could say, what if I gave each bidder at most one item? Then I, again, just need to ask each bidder for each single item, what would be your value if you got only that item? And I can be more creative. I can say, what if I asked every bidder, how much value would you get if you got everything? And please also tell me how much value would you get if you got every single item? And I can try and be very creative with this. And so again, what I'm saying is the VCG mechanism is so general that for any of these restrictions, if you can solve it in polycommunication, you can turn it into a truthful mechanism using VCG. Okay, and so this became the VCG-based framework. And the trade-off here is that if you choose very simple allocation spaces like any of these, then I actually can optimize exactly in polycommunication, so I can use VCG. The downside is that if my allocations are super simple, then I have no reason to expect the best one to be any good. So if I insist on giving each bidder at most one item, that's probably not a very good allocation. It's probably not anywhere close to what the best would have been. Okay, so the catch is to try and balance this trade-off, or that the goal is to balance that trade-off. Okay, so what was known before? So I'm going to emphasize each time that whatever shows up at this slide is the best known deterministic mechanism at all. So this framework is not without loss of generality, but everything that's the state of the art happens to fall into this framework anyway. And I told you that the best thing we knew how to do before was slightly better than trivial. It saved this root log m. Okay, and I'll tell you their mechanisms. It's very simple. So they said, I'm just going to take all the items and I'm going to break them down into log m chunks of size m over log m. So I just take items 1 through m over log m, call that a chunk, m over log m plus 1 to 2m over log m, call that a chunk, and so on. And then I'll just ask each bidder, for every set of chunks, please tell me what your value is. Okay, and so that I can do in polycommunication because there's only log m different chunks, and so 2 to the log m is m, or depending on what the constant is, a polynomial. And then I'm just going to select the welfare maximizing allocation that keeps all the chunks together. Okay, so this is something I can do. I can optimize in polycommunication. And the only question is, how good is the welfare? And I'm not going to prove this, but the proof would fit on one slide. It's not that long. And the answer is m over root log m. Okay, so it saves you a little bit. Okay, and so the new result I just want to quickly state is, on one hand, will not sound super exciting because I'm going to tell you we can change the saving a root log m. We can now save an entire log m. But I'll tell you in a few slides why you should find that slightly more interesting. And I just want to quickly tell you what's the mechanism. So I'm, again, not going to prove this. So I'm going to start off very similar. I'm going to break the items down into chunks. I'm going to ask every bidder for their value for every set of chunks. That's exactly the same. And the only thing I'm going to do differently is I'm just going to repeat this. Think of k as log m, since I'm interested in polycommunication, but I didn't want to write log m every single time. And so I'm just going to repeat this polynomially many times. And I need to be a little bit careful about how I repeat this across different chunks. I'll give you the property in a second. And then it's the same thing. I just select the welfare maximizing allocation. So I'm basically just like trying the previous mechanism. I'm repeating that polynomially many times and taking the best. That turns out to save you another root log n. Okay, and so I want to quickly state, so there's an interesting connection. I don't know if anyone in the room is a learning theorist, but it turns out that there is an interesting connection between all of these VCG-based mechanisms and something that we called shattering, which is similar to the notion of shattering from learning theory. And it turns out that this thing you need all sets of size 2k. There needs to exist at least one collection of chunks such that every item in S goes into a distinct chunk. Okay, so that turns out to be the key property you need. And this is actually entirely a combinatorics question and something that learning theorists think about. And in this case, it's not a hard combinatorics problem because if you just take uniformly random collections of chunks, it works with high probability. But some variants of this are hard. So I just wanted to throw that out as a teaser in case there's learning theorists watching or combinatorists. Okay, so that's the positive result. And then this slide is going to tell you why you should be at least somewhat interested that we saved an extra root log m. So prior to our work, there was also a lower bound. And that lower bound said that, again, if you think of k as log m, that you couldn't do better than m over log squared m. And the other thing we did was we improved that lower bound. So I would say now, whether or not you care about like the difference between root log m, log m squared, at least we know exactly what the answer is. And the answer is exactly, you can do m over log m with the VCG-based mechanism for arbitrary monotone valuations. Okay, so that is, let me just pause here. Okay, so that's the end of kind of like part 1A of the talk, was I wanted to just describe this mechanism and say what's going on. So this is VCG-based mechanisms for arbitrary valuations. And I will now transition to part 1B. So this is still VCG-based mechanisms, but I'm now going to tell you a different setting. And so again, I apologize, there's a lot of context switching, but in exchange, there's no proofs. Okay, so for this part of the talk, I'm going to talk about everything else that was on that initial slide. So this is, you can restrict the valuations to be submodular, subadditive, fractionally subadditive. This basically just means that there's no way that there's hidden complements where you only get value if you get exactly this 7 items. And it's really the case that if you are happy to have 7 items, you must be somewhat happy to have, you know, the left half or the right half. Okay, so what's the best thing known here? So I told you there's a root m approximation. It's the best deterministic mechanism we know. It's VCG based. And again, I want you to contrast that with the constant factor approximations that we have for algorithms. And I'll also tell you their mechanism. So their mechanism is pretty simple. So they say, I'm going to ask each bidder, if I were to give you everything, how happy would you be? And for every singleton, if I were to give you that item and only that item, how happy would you be? And so then you select the welfare maximizing allocation using the information you have. And what this is going to do is it's either going to give all the items to the same bidder, or it's going to find the max weight matching of items to bidders. Okay, so that's their mechanism. And I will tell you, so what did we do? We also improved this. It's also, again, by kind of a very small factor. It's another root log m. And I'm going to tell you the mechanism. And it's definitely a mouthful. But the main thing that I would like you to take away is that the new mechanism does not look like theirs at all. It looks like it is using the previous mechanism I showed you as a subroutine. So I would say, to the extent that if you're planning to remember anything about this section of the talk, that's the takeaway that I would like you to take. I'm going to state the mechanism just to back up that this is the correct takeaway to have. Okay, so the first thing you do is you're going to break down the items into root m over k buckets, and each bucket is going to have root mk items. Okay, so that's new. That wasn't in the previous one. Then you're going to do this previous thing as a subroutine. You're going to break each bucket into k chunks. That's exactly the thing we did before. You're going to repeat this 2 to the k times, so poly and m times. That's the same as before. And then you're also going to repeat this bucketing poly m times. Okay, so the only thing that's added from the previous one is there's this additional wrapper of breaking things into buckets. Okay, fine. So then what do you do for the bidders? You say, okay, for each bidder, I would like you to tell me, first pick a bucketing. So there are 2 to the k different buckets. So there's polynomially many different buckets. So they're going to pick one of those. And then for each bucketing, they have to pick a single bucket. So they are not allowed to get items across multiple buckets. So you have to pick a single bucket for the items they're going to get. Within each bucket, they have to pick a single chunking. So they're not allowed to pick chunks that come from different chunkings. But then within a single bucketing, a single bucket, a single chunking, they're allowed to take any number of chunks they want. Right? So by the time I get to the end, it's exactly the same as before, where I say, well, there's only k different chunks, so there's only 2 to the k subsets of chunks, so you can just tell me everything. But there's a lot of different options for how do they get to that final chunking. Okay, so like I was saying, I think mainly I want this to just be like, read once. Okay, I read it. Probably I'm not going to remember that. But definitely this feels like using the previous one as a subroutine, which is very different than the previous approach. Okay. So that's the algorithm. And the other things I'll state, so I'm not planning to give any details on how we did the lower bounds, but we also improved the lower bound. And here we did not get it all the way tight. So there's still a gap of root log m. And if you're super curious, there's actually, it's related to a combinatorics problem that we weren't able to solve. I don't know if it's a super hard combinatorics problem or if we're just not, combinatorists, and maybe would be easy if we found the right person to think about it. But there's a related combinatorics problem that's related to the last root log m gap, and I'm happy to tell anyone about after. But that's there. And the main thing I'd highlight is just that the prior gap was polynomial in m, and now the gap is just this last root log m. Okay, so that is the conclusion of the entirety of part 1 of the talk. So I'll talk slowly for like 30 seconds or so to give a little bit of context switching time. And so just as a reminder, what I wanted to do there was I looked at a specific class of evaluations called VCG based, and we tried to really nail what is the actual best you could do. And I said, this is interesting because all of the state-of-the-art mechanisms we know are in this class. And now we know, except for this one last root log m, what is the absolute best we can do within this class. Okay, so the next thing I'm going to do is I'm going to pivot. So same problem, communication complexity of combinatorial auctions, still interested in truthful mechanisms and all of that. But now I'm going to try and prove lower bounds on, I'll go here, but now I'm going to try and prove lower bounds that hold for every deterministic truthful mechanism, not necessarily those that lie in a specific class. Okay, so for this section of the talk, I'm going to focus on these XOS or fractionally subadditive valuations. These are the ones that were maximum over additive. So you have a long list of additive valuations. And when I give you a set, you pick the best additive valuation to evaluate it. And I chose to emphasize here, like we really, really know how good the best algorithm is. So we even know specifically as a function of the number of bidders, how exactly does the constant approach it approaches 1 minus 1 over e exactly for n bidders. We have a construction, we know an algorithm, we know that really well. And still the best deterministic truthful mechanism is this slightly better than root m approximation. And the other thing I want to note that I think is, I guess it's cool, but also indicative of how far we are, is if I plug in n equals 2, then that gives me a 3/4 approximation for 2 bidders. But actually, all of these mechanisms, even the randomized one, like there's 1 over log m squared or 1 over root m, that's only interesting if there's a lot of bidders. If there's 2 bidders, then I can always just say, hey, both bidders, please tell me your value if I were to give you everything. And I'm going to give one of the bidders everything. And that will get me a half approximation. Right? So this is actually the best this is the best randomizer deterministic truthful mechanism we know, is just to do that. So we don't know any non-trivial truthful mechanisms, even though this is a pretty cool algorithm. Okay, so this is just a reminder. So now I'm going to focus on unstructured mechanisms. So I want a lower bound that holds for everything. And the main challenge here is we know we have good algorithms. So like no matter how good you are at proving communication lower bounds, you are not going to prove a pure communication lower bound that rules out good truthful mechanisms, because there are good communication protocols. So somehow this means that you need to figure out, how am I going to leverage truthfulness and say I have a lower bound that only applies to truthful communication protocols? And so there's a decent amount of prior work that tried to approach this by characterizing all truthful mechanisms. So for example, if all truthful mechanisms were VCG based, then we know what the answer is. But it turns out that not all mechanisms are VCG based. And so there was a lot of work about maybe 20 or so years ago trying to see, okay, they're not all VCG based, but can we still try and characterize exactly what they are? And I think what we learned from that was largely that there just are weird truthful mechanisms, and we are probably not going to get a clean characterization of all truthful mechanisms. So we need a different approach. Okay, so now I'm going to tell you an approach that was proposed not by me, but that I think is super cool. So I'm going to overview it on this slide. I think to the extent that there is a most technical slide in the talk, I think it is this slide and the subsequent one. Just as a heads up, but I will go through this. Okay, so a concept from economics is called the taxation principle. So what does that mean? So ultimately, every mechanism is a mapping from like my value, Mark's value, Shubhangi's value to what sets do we get? And here's a helpful thing to think through. You can say fixing Mark's value and Shubhangi's value. If I say V, then I will get set S and pay P. Keeping them fixed, if I say valuation W, I will get set T and pay Q. And if I say a different valuation, I'll get set U and pay Z, right? So I can, right, because the mechanism is a mapping that takes all of us in. If I fix them, then I can list for each thing I might say, what's the outcome I'm going to get. Okay, so I'll call that thing a menu. So fixing them, what is the list of things that might happen to me based on my valuation? So now what's true about any truthful mechanism is it better be the case that when I participate in the protocol honestly, I get my favorite thing on the menu. So why is that? If I don't get my favorite thing on the menu, then I've explicitly found here is something Shubhangi and Mark could have said. And then if I'm honest, I get this set, but literally something else on the menu says, if I would have said this other valuation instead, I would have gotten a set I like better. Okay, and truthful exactly means that should never happen. Okay, and so one more example, because this is, I think, a tough definition, is if I think about the second price auction. So that is an auction where I ask every bidder for a single item, please tell me your value for that item. Whoever says the biggest number, I give them the item, and I charge them the highest number besides themselves. Then what the menu will look like is no matter what everyone else says, there is some maximum number among them. And no matter what I say, I will either not get the item and pay nothing, or I will get the item and pay that highest bid. So there are two possible things that will ever happen to me. So that's my menu. Okay, and so in Dobzhinsky's paper, he proposed that looking at the max overall bidders of the log of the number of distinct menus was an interesting thing. I'll tell you why that's interesting on the next slide. Okay, so forget about the max overall and the log of the whatever, but this is counting the number of distinct menus. So what does that mean? That means that for every possible things that Mark and Shubhangi might do, that induces a menu for me. And so I'm asking how many different menus can Mark and Shubhangi induce for me? So he said, that's an interesting thing to count. Okay. All right, so let's just do another example to get comfortable with this. So if I have a second price auction and everyone's got to submit an integral bid, then when I look at this menu up here, there are n+1 different possible menus that I might see, right? Because my menu is always of the form, maybe I get nothing, or maybe I get the item and pay X, and X is some integer between 0 and n+1. So therefore, there are n+1 different menus. The taxation complexity is log n+1. Fine. As another example, it turns out that if you run the VCG mechanism with two bidders, then every different valuation of Mark would induce a different menu for me. So that means that if Mark has capital V different possible valuations, then I see capital V different possible menus. Okay, fine. Okay, so why is this a useful definition? So first, let me say, why is it not useful? So it turns out that there are protocols that have communication complexity that has nothing to do with its taxation complexity. Okay, so here's just a fact. I'll ask you to, so gross substitutes is a valuation that's a mouthful to define. I'm not going to define it. You don't need to know what it is. I'll just ask you to kind of, trust me, here's as a fact, there are doubly exponentially many different gross substitutes valuations. So that means that if I run VCG with gross substitutes valuations, the taxation complexity is a log of that, which is exponential. Here's another fact that I ask you to trust me on, is that you can execute the VCG mechanism in poly communication for gross substitutes. So what does that mean? That means I have a protocol. It's got a very high taxation complexity. So there's lots and lots and lots of different menus, but I can still run it quickly. Fine. It turns out the super cool thing is that if your mechanism is truthful for a rich enough class of valuations, then this can never happen. And in particular, what Dobzhinsky showed is that the taxation complexity lower bounds the communication complexity, but only for truthful mechanisms for rich enough valuation classes. So what does this mean? This means that if you want to prove a lower bound that only holds for truthful mechanisms, a reasonable thing to do is to lower bound the taxation complexity you need to solve a problem, because that will not lower bound the communication needed by an algorithm, but it will lower bound the communication needed by a truthful mechanism. So that was the cool framework that came out of that. The second cool thing he showed is that actually there's even a further step to this reduction. So he showed that if you want to focus on two bidders, then if there's a good truthful mechanism, this says that good truthful mechanism, which has low communication, must have low taxation. He said also there must exist, in addition to having low taxation, there's another protocol that must get good welfare, and it must, that protocol you can assume is simultaneous. Okay, so what does simultaneous mean? It means that each bidder sends exactly one message simultaneously, and based on only that message, the designer says, here's what sets I'm going to give you. Okay, so an awesome new approach just based on this is you could say, hey, if you can just get someone who's really good at communication complexity, perhaps they're your postdoc supervisor, and you can work with them, and you can say, I have a concrete communication complexity problem, which is I just need to show a lower bound on simultaneous protocols for this well-posed communication problem. That has nothing to do with incentives. Then we can get the first separation between truthful and non-truthful communication if we can just show that simultaneous protocols aren't as good as interactive ones. Okay, so what I was hinting at there is that, so I saw this talk in 2015 at Simon's by Dobzhinsky. And this is what got me interested in combinatorial auctions. And I, at the time, thought, I'm immediately going back to Princeton. Mark is my postdoc supervisor. He's like one of the best communication complexity people in the world. I think I just need to tell him this problem, and then we'll solve it. And then this will be great. I can go back to my econ CS friends, and then, you know, they'll like me. And so what happened is, so eventually that did happen. But it turned out it was actually a really hard problem. And if you are a communication complexity person or curious, like what made it so hard, there are some kind of formal barriers that made it very hard. But eventually I did get there, or we did get there. And this is also the paper that kind of got me to learn communication complexity from Mark. And now I like actually learned enough, I can do communication complexity on my own. So I thought that it was a very meaningful project for me and was a good opportunity to kind of like learn, you know, like from Mark when I was a postdoc, and I'm definitely super appreciative for that. So in terms of what the result is, so we were finally able to show that there is a small constant separation. So no simultaneous protocol can do better than 3/4 minus 1/240, whereas an interactive protocol can get 3/4. And so now we know that there is a small constant separation between what you can do with deterministic truthful mechanisms and what you can do with algorithms. And so that is, this small constant is the best thing we know at this point. So at some point, I'm still working and hoping that we will get that, you know, to be all the way to the separation that exists, which is like roughly root log m, or sorry, root m. But at present, it's this small constant. Okay, so very last context switch. So this is going to be the 2B part of the talk, and then I will wrap up. Okay, so here's one last definition, but it's a short one. So another particularly simple class of valuations is what's called single-minded. So what is that? That means there's a set of items. I want exactly that set. I don't want any subset. If I don't get everything, I'm not happy. If I get more stuff, I'm just going to throw it away. There's a set of items I like. My value is V. And so my value is, if I get this set, I'm happy. I get value V. If I don't get this set, I get nothing. Okay, so single-minded bidders are succinct in the sense that they are very easy to communicate. So they can be hard for combinatorial optimization if I care about actually designing an algorithm. But in terms of information, it's super easy. I have to tell you one set and I have to tell you one number. Okay, so that's very easy to communicate. And so some intuition I had when we were starting to play around with trying to get hard instances is that maybe like adding single-minded bidders to an existing combinatorial auctions problem maybe should not make communication much harder, right? Because I'm adding some input to the problem that I can just immediately share, right? So communicating as a single-minded bidder is not hard. No matter what the protocol is, you just tell everyone all of your information. And this isn't, this isn't like a formal claim because, they do change the problem that everyone else is solving because now there's a single-minded bidder in play. But like I thought like that, that can't be real. That must just require, some work to get around. And so then the last thing I'm going to tell you is just a statement of some results. So we actually looked into this and it turned out to be more interesting than we were expecting. And so this is just in terms of algorithms first. So if there are no single-minded bidders, then there's this older paper that gets a half approximation. But it turns out that if you throw in some single-minded bidders, then all of a sudden the best you can do is a third. Okay, so they actually do meaningfully change the problem. This algorithm, given that there's a half approximation for a subadditive, getting a third approximation with single-minded bidders, that is trivial. The lower bound is the interesting part for this. And for XOS, it turns out that this 1 minus 1 over E changes into a half. And in this case, both the algorithm and the lower bound are interesting. That I forget what the number is, but like if you just did something trivial given this and throwing in some single-minded bidders, you would not get a half. But it turns out a half is the right answer. And then the last thing I'll say is we also looked at the reason we started thinking about algorithms for this is because, like I mentioned, I've been stuck for like 10 years trying to prove lower bounds on deterministic truthful mechanisms that are bigger than a constant. And after, I was super excited 5 years ago when we finally got a small constant for 2 players and a framework that only works for 2 players in the first place. So we were trying to think of how can we get around this. And so something we showed is that if you have bidders that are subadditive or single-minded, then the best you can do with a truthful mechanism is about 0.366. And if you only have 3 bidders, then definitely adding single-minded bidders doesn't make the problem any harder because you can just exhaust over like, here's a single-minded bidder. Do I give you your set, solve the problem on the rest? Or do I not give you your set, solve the problem on the rest? So you just have to do, 2 extra work. Okay, and so this is the only separation we know that goes beyond 2 players, because I mentioned the 2-player result like uses a framework that only works for 2 players. Okay, and so as maybe a summary is that we're still very stuck. I'm still working very hard. I don't know how long it's going to take to, have more interesting results on these slides, but we're still at the stage where we have constant separations, and I think the right answer is probably that maybe these algorithms I showed you may very well be the best truthful mechanisms, but it's just very hard to prove lower bounds. Okay, so just to summarize, so what did I do? I showed you, tight and almost tight analysis of this class of VCG-based mechanisms. I told you that there is a separation between what you can do with polycommunication algorithms and truthful mechanisms for 2 players. And then I also briefly told you about adding additional succinct bidders, and it's kind of surprising that actually did change the problem in an interesting way. And then in terms of, like I mentioned, I'm still working super hard on a lot of this stuff, and I'm a little bit trying to give talks like these because I do think that, especially for people who are really into combinatorics or communication complexity, I do think there are just hard problems in combinatorics and communication complexity lying around that are accessible without knowing all of the econ that motivated these in the first place. And I would say definitely, I think kind of like the big question is just like, I think that probably those mechanisms I showed you are roughly the best you can do. And all we can do is say, well, you can't do, 1 over 240 close to, this small constant of 3/4, and probably you can't even do better than root m or something like that. Okay, so I think that's it. Thanks a lot to everyone for listening, and then I'll wrap up here. Thanks.